So, we have already discussed individual dislocation properties, we have seen a overall dislocation property, but so there were two different dislocations, edge and screw, but we also said that in reality you will not have a true edge or a true screw dislocation. What you really have is most of the time like this. So, let us say that and we also said that it cannot the dislocation cannot start and end inside a crystal, it must either form a loop or must terminate at a grain boundary or a surface. So, let us assume that we have a loop like this, okay, and this if it is a loop, it is one dislocation. Okay, let me so we are assuming that this is one dislocation, there is no start and end. Just the way it has been drawn, there may look like a start and end, but that is just artifact of our drawing. So, there is a loop like this, and since it is one dislocation, you remember one of the general characteristics that we described is that the Berger vector must remain constant. So, for this whole dislocation there will be one Berger vector and it must lie in this particular plane if we are talking about a dislocation glide dislocation loop. So, the Berger vector would be like this. So, this is the Berger vector in the plane, and this type of dislocation loop is called glide loop. We will see that there can be another kind of dislocation, but for the time being let us stick with this. Let us try to understand more details about this. So, let us look at different aspects. This is the Berger vector, and the line vector is how line vector is continuously changing along this line. So, somewhere around here the line vector would be let us say we have taken a convention that line vector is going like this. So, it cannot change sense arbitrarily. So, it is continuously going like this. Now, at this point, somewhere around this point, the line vector, as you would see u, it is parallel or in fact anti-parallel to b. Similarly, somewhere over here the line vector would be parallel to b. Somewhere over here you would see that the line vector is exactly perpendicular to b, and somewhere over here again it is exactly perpendicular to b. So, remember what does that mean? What does the parallel and anti-parallel mean? When is the b parallel or anti-parallel to u? When it is a screw dislocation. So, it is a this particular point is a screw dislocation, pure screw dislocation. This particular point is a pure screw dislocation. This particular point is a pure edge dislocation. Now, this one similar to that one is also a pure edge dislocation, meaning in a loop like this, if it has continuous without lots of minimas and maximas, then there are only certain number of points certain number of points are pure edge or screw. So, that I hope that you can now realize from this, and most of it is actually a what is it? Most of it other than these points. So, everything other than these points is a mixed dislocation. Can you imagine a loop where you have only edge and screw dislocations? Think about it. So, you have to have the u vector either parallel or perpendicular. So, let us say I have already given you that the b vector is like this. Now, you have to imagine a dislocation loop which has only lines which can either be parallel to b or perpendicular to b. So, if it will not take much of imagination that you can actually have a dislocation loop like this. So, in theory you can have So, these will be edge, these will be screw and all of it, not just point. So, in theory you can have a pure edge and pure screw dislocation even if it is forming a loop, but in reality this is not what you would see. In reality you would have something more like this. So, there will be only fixed number of pure edge and pure screw and remaining of it will be mixed dislocation. So, now we have termed mixed dislocation so many times. It is time that we draw a mixed dislocation. How should a mixed dislocation look like? We cannot draw all the planes. I mean, we have seen it in the 3 dimension, but what I am talking about is inside it. What we were able to look at in the 3 dimension were only from the outside. How would it look like in the inside? How are the atoms arranged when you have a mixed dislocation? So, we will try to draw it over here. So, let us say this is the set of atoms just below the plane which has slipped. So, these are arranged in a well coordinated or well periodic manner. There is no displacement in this plane of atoms. So, these are the, we are drawing only a very small number of atoms. In reality what I have drawn here would be actually extended to a much larger set of atoms, that as you would see what we will call as transition from edge to mixed to screw would be taking place over hundreds and thousands of atoms, but we are just trying to draw a schematic or understand what exactly goes on inside the atomic layers. Now, next what I will do is I will draw line to show where the atoms on the layer above it would lie. So, let us say the first this layer of atom, this lies perfectly, matches perfectly. Now, let us say the second layer of atom, this has so there is already, you can see some displacement over here. So, there is another displacement over here and yet another and yet another. So, if I were to draw atoms onto this, the atoms on the top layer are lying something like this. So, this one lies just above it. Over here some of it are matching, others are getting displaced. Similarly, the atoms over here are matching, but some others are still getting displaced, and as you shift you see that there is a certain kind of pattern to it. What is the pattern? Here on this side, as you would see, what would you call this? If you look at it, there is a extra half plane on the bottom and there is a missing plane on the top. So, this is nothing but a edge dislocation at the outset here. So, this is a edge dislocation. We are talking about just the end, not the inside part. Now, when you look over here, what you see is that there is a screw kind of character, meaning that when you rotate, when you go clockwise, you see that you are coming out. So, this is a screw dislocation, and to be fair, to draw it along the, or to be accurate, the line vector would, let us draw something which would make sense. So, here we have the edge screw dislocation, here we have the edge dislocation. So, the two dislocations at the extreme end, but inside if you look at it somewhere over here, can you define any particular characteristics? It is not really. There is, you can if you look at it one way, it would look like there is extra half plane. If you look at it other way, it would look like it has shifted to give it a screw like character. So, in somewhere in between these, what you would see is that it is a mixed character, and this is what we are referring to as our mixed dislocation. So, your core line would go something like this. So, this is how your mixed dislocation would look like. From if we had drawn only a line in the not without the atoms, then it would look something like this. So, we have drawn a quarter of the loop of what we had drawn earlier, and at this particular point we have here screw, and at this particular point we have edge, and everything in between is mixed dislocation. So, now you can realize that what kind of atom arrangement is there in the mixed dislocation, and it would be better if you can draw some of these to actually get a feel of it, because most of the time in the books what you will see is from how it will look from outside. So, from the outside, of course, on one side it is edge, on the other side it is screw, but is it actually feasible to draw a structure like that is what you would get to know when you draw something like this. So, I will suggest that you draw a couple of these drawings with different orientation of edge and screw, sometimes RH right handed screw, sometimes left handed screw, sometimes the edge dislocation with extra plane on the bottom and sometimes with extra plane on the top side. So, that will give you a good understanding. And over here, so if this is the direction, the Berger vector is like this and Berger vector remains constant. So, Berger vector here is like this. So, this is again as you would expect, Berger vector is perpendicular to u here, Berger vector is parallel to u here. So, B is like this. So, no surprises here, of course, this is what you expect, the Berger vector to lie parallel at the screw dislocation side and perpendicular to the line direction at the edge dislocation side, and everywhere in between what you have is mixed. So, how would it look like, or how would it work when you have a mixed dislocation, meaning in terms of finding the character? Can we resolve? There are two methods to resolving. So, let us say this is a dislocation line, we are looking at a very small segment, but what we know is that the Berger vector is going something like this. Now, the line direction at each point is nothing but tangent of it. So, if let us say we talk about this particular point. So, at this particular point there is angle theta between. So, let us say this is the tangent to this point P. So, what we are trying to do here is resolving. There are two methods to resolve a dislocation into edge and screw. One is resolving Berger vector B, and we will see the other method is resolving line direction u. So, first let us look at what we do in resolving B. It is very simple, you have to just take component of B in parallel and perpendicular to u direction. So, this is your Berger vector B. So, we will draw it now. The orange one that I have drawn earlier is the perpendicular, it is the tangent to the line which is u vector u, line vector u for the point P, and the red ones that I have drawn. So, this red is the total Berger vector, this red is perpendicular to u. So, it means this represents B edge, this is parallel to B. So, this means B screw. And it is not very difficult to see that the B edge, if here the theta is given like this, B edge is equal to B sin theta, and B screw is equal to B cos theta. So, if anywhere you have to say or take into account calculations of edge work of edge and screw, then you can now see, you can just put B cos theta for this particular dislocation, which is a mixed dislocation, and simultaneously take b sin theta as the Berger vector for edge dislocation. So, this would be useful for as you would see later for calculation of stress, strain and energies. The other method that we said, which is not you can say used more mathematically, but it is more from the point of understanding or conceptual, is resolving line vector u. So, we will take the same dislocation line like this. We are talking about the same point P, and this is our line vector u, and we already know that the Berger vector is like this. So, now what we need to do is just okay, so we are also aware of this angle theta. So, what we need to do now is just take components of this u parallel and perpendicular to b. So, this is u cos theta, this is u sin theta. So, now you have basically divided or dissolved line dislocation component, a small component, into parts which are parallel to Berger vector and perpendicular to the Berger vector. Now, when the part which is u cos theta, which is perpendicular to the Berger vector, this part represents effective extra half plane. And this part u cos theta, this represents effective screw component. This is, as I said, useful for conceptual understanding. You will at least in our work we will not be using resolving u method, but resolving b method. So, this is mixed dislocation, and now this will also help you understand why we are always talking about screw dislocation, edge dislocation, when in reality what we have is a mixed dislocation. Because now you can see that we can easily resolve at any time any mixed dislocation into edge character and screw character, and even do mathematical manipulations, basically trying to understand stress strain. We can resolve it into stress component, into edge component and screw component, get stress, strain, energy, all everything, and just we need to add them in a proper fashion, and we will be able to get every information about that mixed dislocation. So, it is nothing to be intimidated about, that what we have is a mixed dislocation and not a pure edge or screw dislocation, and we can still continue our understanding about pure edge and pure screw dislocation. So, before I move on to understanding more of the pure edge and pure screw dislocation, we said there was something called as glide loop. So, we said glide loop is when you have glide loop is the one where you have Berger vector in the plane of the loop. So, over here, like I said, this is perpendicular. So, there is, you can imagine there is a edge dislocation. On the other side also there is edge dislocation of opposite character, and since you are over here, there will be some screw dislocation, which will be either, let us say it is right handed side, and if you go to this side, there is a pure screw dislocation there is at one point, and it will be left handed side. So, the edge character is continuously changing, or and the drawing of how the atoms are arranged is something we have already seen. Now, the other one is what is called as prismatic loop, And by now you should have realized what it will, how it will be different from the glide loop is that the Berger vector would be perpendicular. So, it is perpendicular going in or out of the plane. It is not in the same plane, it is either going in or going out of the plane. So, the Berger vector is like this. Now, what does that mean? Can you imagine how the dislocation here should look like if you have the Berger vector over here? First of all, you realize that this is Berger vector and the line vector is like this. So, line vector is moving on this particular plane, it is rotating somewhere over like this, like this, like this, like this in at different points, but Berger vector is always like this. So, what does this mean? That the Berger vector is always perpendicular to line vector. Now, that is very surprising. So, in a loop we have a completely edge dislocation because the Berger vector is lying always perpendicular to the line vector. So, this is a very interesting loop. Now, how does it look like, or how does it the atoms, how are the atoms arranged here? It is not very difficult if you think about a little bit. What you will realize is that what it is that either you have an extra set or extra loop of atoms present, or there is an extra loop of atoms missing over here. So, it is more like vacancies which have condensed in this region. So, this is the condensed vacancies and there is extra plane all around. So, you can draw it something like this. So, there is extra half plane, extra half plane. And as I said, the other way, in this particular case what you have is extra half plane is outside this loop. The other configuration for the prismatic loop is when you have the extra half plane inside this. So, it is an extra set of atoms which have condensed over here, and in this particular case you will draw it like this. So, one of them will be positive B, other will be negative B. So, this was coming out, now this is going in. So, this is a prismatic loop, and it has only, in this particular case when we looked at glide loop, it has pure edge, pure screw and mixed. But over here if you come, what we have is only edge dislocation. It is only this, it is only that it is oriented different from what you see over here. So, prismatic loop is very different from a glide loop, and even its characteristics when it comes to moving is very different from the glide loop, and we will discuss those when we come to movement of dislocations. So, now that we have understood the dislocation in a general way, we have looked at edge dislocation and screw dislocation, their individual characteristics and some of the other properties, for example, that what is the relation between B and U and all those additional parameters. We have also looked at there is nothing called as pure edge and pure screw in most of the time, and it is only mixed dislocation, but we can still understand pure edge and pure screw. So, with those understanding, now we will move on to develop our understanding of the elastic continuum model, which is used to understand energy, stress field, strain field and the energy stored around a dislocation. So, next what we need to do is develop our understanding of elastic continuum model, which is used, what is it used for? It is used to understand stress fields, strain fields, and energy stored in these dislocations. So, as you will see, it is kind of irony that when you do deformation on a material, plastic deformation, it leads to generation of dislocation, and the energy that you have put in, the work that you have done gets stored, fraction of it, in the form of elastic energy around these dislocations. So, this energy that we are talking about, these are elastic energy in and around the dislocations. And to understand this, we will need this elastic continuum model. We will just explain briefly we will just go through the basic concepts of elastic continuum model. What first of all, you know the term elastic, meaning it can release, it can come back. What is continuum? Continuum means that it is continuous. There is no, when we are developing these models, we are ignoring that these solids are present as individual atoms. Instead, we assume that it is a uniformly distributed with uniform density of material. So, the properties are, you can say, isotropic, and it does not change from one point to another. For example, if we were to really go in depth, what we realize is that the masses are stored in atoms. So, in between the two atoms there is no mass, and therefore, the properties are very different when you go from one atom to in the space in between these two. But in the continuum model, we are assuming it is a one uniform material with uniform density, and there is no discrete object inside it. There is continuous distribution of the material. So, no discontinuity, and hence as a model we are assuming no atoms, etc. But of course, there are limitations. When you go very close to a dislocation, this model breaks down, and we have to resolve to, you can say, empirical understanding at that end. So, now having said that, what are the stress and strains? How do we define the stress and strain in a system like this? So, there are stress and strain is actually, as you would know, that not a vector or not a scalar quantity, it is a tensor quantity. So, it has 9 different components. So, if we look at a small component of the material which has which is in a cubic form, because we are because let us say we are taking a x, y and z coordinate system. So, this is y, this is x, and this is z. So, we have x, y and z components, and for this particular small element from the material, we have taken a small element with x, y, z coordinate. We can define stresses along different directions. The usual way is when we say sigma ij, it means sigma in I direction of j plane. So, you will have stresses along all the 3 different directions. I will leave you with this drawing. You will have to tell me where will be the sigma x y, sigma y z, sigma z x in all this, and in the next class we will continue with this, and you will see where to fill in sigma x y, sigma y z using the understanding that is already given over there. So, we will meet in the next class.